Okay, welcome guys. This is 3.7 L'Hôpital's rule, not L Hospital, L'Hôpital, okay? And we use L'Hôpital's rule on limits to make them easier. But the only way we can use L'Hôpital's is if we come across a certain type of form. That form is called indeterminate. It has to be an indeterminate form, and those forms are 0 over 0 or infinity over infinity. So we are looking for those forms. If it's not indeterminate, we cannot use L'Hôpital's. Okay? So that's the only way we can use L'Hôpital's. All right. So for L'Hôpital's rule, suppose that f and g are differentiable and g prime of x does not equal 0 near some number of a. Suppose that the limit of f of x is 0 and the limit of g of x is 0, or the limit of f is infinity, or the limit of g of x is infinity as well. Then the limit as x approaches a of f over g is equal to the limit of the derivative of f over the derivative of g. So what this says is everything I just told you about a minute ago. In order to use L'Hôpital's rule, the numerator must be 0 and the denominator must be 0. Or the numerator must be plus or minus infinity and the denominator must also be plus or minus infinity, because these are indeterminate forms. And if they are indeterminate forms, this means we get to use L'Hôpital's, which means you get to take the derivative of the numerator and you get to take the derivative of the denominator separately. No quotient rule, okay? So, again, L'Hôpital's only works on indeterminate forms. So if we get an indeterminate form, we can use L'Hôpital's. All right, and this is also true for one-sided limits and limits at infinity. Okay, so we want to practice using L'Hôpital's. So we'll start with number 1. In order to use L'Hôpital's, we first have to see if we get something indeterminate. So our very first step, always with limits, is, hey, plug the number in. Let's go ahead and plug in 1, and let's see what happens. If I plug in 1, I get the natural log of 1 over 1 minus 1, which gives me 0 over 0. And now this is what we're looking for, because this is an indeterminate form. And since it's an indeterminate form, we are now allowed to use L'Hôpital's. So we're going to use L'Hôpital's. I'll say LH. We're using L'Hôpital's. So one fun way to see this is that if we need to fix this limit because it's an indeterminate form, we are going to take it to the hospital. Not just any hospital, the L'Hôpital. Give it a try. Okay, so we apply L'Hôpital's, which means now we get the limit as x approaches 1 of the derivative of this numerator, which is 1 over x, over the derivative of that denominator, which is 1. This means we get the limit as x approaches 1 of 1 over x And is it now safe to plug in 1? That answer is yes. We can now plug in 1, which means you get 1 over 1, or just 1. So by L'Hopital's, our limit is 1. So with that being said, again, if we're taking the derivative using L'Hopital's, it is just the derivative of the numerator and the denominator separately. We are not using quotient rule. Okay. And that's what we come across. And of course, you can check this by making an XY chart, maybe algebraically manipulating it somehow, but L'Hopital's is so much easier to use. It helps us get us limit a lot faster. But remember, we have to be indeterminate. Okay. Perfect. Next. The limit as x approaches infinity of e to the x over x squared. Well, again, to determine if we need L'Hopital's, plug it in infinity. If I plug in infinity, I get e to the infinite power over infinity squared. Well, that is just infinity over infinity. And this is an indeterminate form. This is indeterminate, which means since it's indeterminate, we get to use who? We get to take him to the hospital to meet Dr. L'Hopital. Hey, that works better. There you go. So we take him to the hospital and we apply L'Hopital. So this means now we get the limit as x approaches infinity of the derivative of the numerator, the derivative of e to the x is e to the x, over the derivative of the denominator, 2x. Now, again, plug in infinity. Let's see what happens. We get e to the infinite power over 2 times infinity. That's still infinity over infinity, which means, again, we get another indeterminate form, which means that 1 dose of L'Hopital's wasn't enough. It needs 2 doses of L'Hopital's. Great. So we take them to the hospital again, and now we have the limit as x approaches infinity of the derivative of the new numerator, e to the x. So that derivative is still e to the x over the derivative of the other denominator, 2x. That is just 2. Okay. All right. And now plug infinity in again, and we get e to the infinite power over 2, which is just infinity over 2, which infinity over 2 is half infinity, or it is still just infinity. And there's our answer. Boom. So with that example, if you keep getting an indeterminate form, you can keep using L'Hopital's, okay? You can keep using L'Hopital's. Let's keep going. All right. 3. Same thing. Plug in infinity. You get the natural log of infinity over the cube root of infinity. Well, the natural log of infinity is infinity. And the cube root of infinity is still infinity, right? The natural log looks like this. And if x is headed towards infinity, then the natural log must also be headed towards infinity. And the cube root looks like this. And again, if x is headed towards infinity, then the cube root is also headed towards infinity. Which means we get an indeterminate form, which means that it needs some medicine. We need to take it to the hospital. So we go get some L'Hôpitals, okay? All right, maybe now it's just corny, but maybe now you get it. All right, so we apply L'Hôpitals, and we have the limit as x approaches infinity of the derivative of the natural log of x, 1 over x, over the derivative of the cube root of x. Now remember that the cube root we must rewrite as x to the 1/3. So the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Oops. Okay. So now, cleanup time. This is still 1 over x. And now I'm going to rewrite this as 1 over 3x to the 2/3. Fraction over a fraction, we multiply by the reciprocal. 1 over x times 3x to the 2/3 over 1. Cancel, cancel. I have bad notation because this should still be the limit as x approaches infinity. This should still be the limit as x approaches infinity. Bad me, okay? All right, so then cancel, cancel. You get the limit as x approaches infinity of 3, what's this gonna be? Who's bigger? Down there, right? So you're gonna get 3 over x to the 1/3. Because right here, x to the 2/3 over x, that's x to the 2/3 over x to the first, is x to the 2/3 minus 1. That becomes 3 over 3, which gives me x to the negative 1/3, which becomes x to the 1/3 down in the denominator. Okay, in case you were wondering. Okay, and now plug in infinity. What did I just do? Okay, plug in infinity. and we get 3 over infinity to the 1/3, which just becomes 3 over infinity. And we know from limits that any number over an increasing large denominator, that limit is going to equal 0. Because this statement looks like the limit as x approaches infinity of 1 over x to the n. And that always, always will equal 0. I'll leave that for you. Okay, perfect. So that's just 0. Next, 4. Same thing. Plug in 0. Tangent of 0 minus 0 over 0 cubed. Tangent of 0 is 0. So this becomes 0 over 0, which is, wrong color, oh well, indeterminate, which means we get to use L'Hopital's. So we use L'Hopital's, and you get the limit as x approaches 0 of the derivative of the numerator. Derivative of tangent is secant squared x minus the derivative of x, which is 1, over the derivative of the denominator, 3x squared. 3x squared. Okay. Now, let's see what happens if we plug in 0, right? Let's see what happens when we plug in 0. Okay. So this becomes secant squared of 0 minus 1 over 3 times 0 squared. All right, so this means that secant at 0, well, secant's the reciprocal of cosine. So cosine at 0 radians is 1, and the reciprocal of 1, which is secant, is still 1, and 1 squared is still 1. So this becomes 1 minus 1 over 0, which is 0 over 0. Which means, again, we are indeterminate. Which means we get to use L'Hopital's again, right? We get to use L'Hopital's again. All right. So with that being said, let's see. We must take that derivative one more time. So this means that L'Hopital's one more time. And when we take our derivative, let's look at secant squared x, right? Let's look at secant squared x. Okay. Yes. So for 1 second, you're going to probably want to rewrite this as secant x squared. So when we take that derivative, it's going to have to be chain ruled. So this will be 2 secant x times the derivative of the inside, which is secant x tangent x, okay? Secant x, tangent x. Okay, so with that being said, now we know what it is. So I'm just going to erase that for a second. Okay. Here, I'll leave that. I'll leave that. I'll have to get rid of this and this part. So when we do this again, you get the limit as x approaches 0 of 2 secant squared x tangent x. Right? That's what that becomes. 2 secant squared x tangent x all over 6x. All over 6x. Okay, now what we do with this is you can plug in 0 now, but the whole thing will 0 out. So now we want to see, can we fix this by limit properties, by trig limit identities that we've done before? And the answer is yes. I can rewrite this limit as the limit as x approaches 0. Now the only function that's fine here at 0 is secant squared. So this means I can rewrite this as 2 secant squared x times the limit as x approaches 0 of tangent x over 6x. Tangent x over 6x. And again, I'm only allowed to do this is because, well, the numerator is connected by multiplication and they're over the same denominator. So I'm allowed to make the split. So now what you should probably notice is that this limit expression, my goodness, stop it. This limit expression looks like something we've seen before. The limit as x approaches 0 of tangent x over x. And that just equals 1. That just equals 1. So this means that if we come over here, how much room do I have? Oh, I got a lot of room. Okay. So this means, with that being said, where am I? Yes. So this means when I take the limit, I should get 2 times the secant squared of 0 times, and all that's going to be left from this limit I have right here is this tangent x over that x is going to 1. So all that's going to be left is times 1 over 6. And once again, secant is the reciprocal of cosine. So cosine at 0 is 1. Secant is the reciprocal of cosine. So secant at 0 would be the reciprocal of 1. And the reciprocal of 1 is just 1. So that means that if I went one more step, this would become 2 times 1 squared over 6, which is just 2 6, which is just 1/3. And there you go. Not indeterminate that time. You get 1/3. Okay. Perfect. 1/3. Seeing if there's another way to do this, like an easier way. So Let me see. Tangent over that we need to have x over 1 over x squared, so no. Secant squared x over 3x squared, no. That's 0. Oh, that's right. Yeah. So one way we could have fixed this already is remember that, what is it? It's the identity. So I'll go here. So if I brought this out, remember that if I have cosine squared x plus sine squared x equal to 1, if I divide everything by cosine squared, this becomes 1 plus tangent squared x equals secant squared x. And if I move that 1 over, I get tangent squared x equal to secant squared x minus 1. So with that being said, that's all I really want to keep. So let me change this up. So optional route number 2, let me put this in little identity parentheses, and let's say that I'm going to say this is option 2. You now have the limit as x approaches 0 of secant squared x minus 1 over 3x squared. But now we know that by identities, this becomes tangent squared x from everything I just shown you above. So this becomes the limit as x approaches 0 of tangent, too many x's in there, 3x squared. There you go. Of tangent squared x over 3x squared. Which means that if I rewrite this one more time, I get the limit. Actually, I'm going to pull out the 1/3 first. I get 1/3 times the limit as x approaches 0 of tangent x over x squared. Well, just like I said here, this tangent x over x is just like that. So guess what that whole limit becomes? That just becomes 1. So this becomes 1/3 times 1 squared, which all is still 1/3. And that was proven a little faster by identities. The first route works just as well. You didn't have to know identities, you just had to know derivatives. And one little limit identity, one little limit trig identity. Okay, perfect. So know your identities, right? All right. Next, 5. X approaches pi from the left as sine x over 1 minus cosine x. Again, always plug in first. So we get the sine of pi over 1 minus the cosine of pi. Sine at pi is 0 over 1 minus cosine at pi is -1. This becomes 0 over 2, which is just 0. Look at that. No L'Hopital's needed. Okay. Perfect. Should learn how to use my space a little better, huh? Well, at least it fits in there. Okay. All right. So now another thing we can look at when using L'Hopital's is called indeterminate products. If the limit of f is 0 and the limit of g is infinity, then it is unclear what the value of the limit of f times g of x will be. This kind of limit is called an indeterminate form of 0 times infinity, right? Because 0 times infinity is not 0. That's indeterminate, okay? And we can deal with this by rewriting the product of f and g as a quotient. F times g can be written as f of 1 over g or g of 1 over f. You have to play around with it to see what function you want in the denominator. Determining that will make your derivative using L'Hopital a lot easier. Because the question is, well, how do we know which one? You'll know. You may choose it the wrong way and you'll be led down a rabbit hole. But that's the whole process of learning. We're not supposed to get it in one try. Okay, so once again, let's evaluate this limit at 0. This wants it 0 from the right. So this means that if I plug in 0, this becomes 0 times the natural log of 0 from the right. I mean, I could put the little plus sign in here, but x at 0 from the right is just 0, right? So we don't need that in there. The one that really matters is the natural log of 0. Because if we are approaching 0 from the right on the natural log function, if I were to draw the natural log function again, the natural log function looks like this. And here's 0. If we are approaching 0 from the right side, right? We're approaching 0 from the right. This tail is headed towards negative infinity, which means this becomes 0 times negative infinity, which happens to be indeterminate, okay? Because it's 0 times negative infinity. So that means if we get an indeterminate form of 0 times infinity or negative infinity, we get to use L'Hopital's. Okay. So bringing it over here, we get to use L'Hopital's, and that means we're going to rewrite this as a quotient. We're going to rewrite this product as a quotient. So first, the limit as x approaches 0 from the right. And now when we rewrite this as a quotient, I'm going to tell you this, keep the natural log in the numerator all the time, majority of the time. If you put that natural log down in the denominator, good luck. Okay, it'd be worth some practice though. So when I rewrite this as a product, as a quotient, from product to quotient, this is going to become natural log x over 1 over x. This is all I'm following right here, okay? Or maybe it's this one. You get the point. Okay, now before I even take the derivative, because this is somewhat L'Hopital's, all we're doing right now is rewriting the product of two terms as a quotient of two terms. So I want to clean it up. I want to make it look pretty. So I'm going to rewrite this as the limit as x approaches 0 from the right of the natural log of x over x to the negative 1. I am just rewriting it algebraically. No L'Hopital or derivatives have been used at all yet, okay? Okay, which means now we are ready to apply L'Hopital's rule. So we will take the derivative of the numerator and we'll take the derivative of the denominator separately. Now we get to do it. So the limit as x approaches 0 from the right, and I want the derivative of the natural log of x. That is 1 over x over the derivative of x to the negative 1. Negative x to the negative 2. Okay. Cleanup time. Am I using my room appropriately? Yes, in a way, because maybe we'll have to apply L'Hopital's again. So I think we're still good here. Now this becomes the limit as x approaches 0 from the right of 1 over x. I'll do it all step by step. Why not? I'm here. We're here, you're watching the video. 1 over x over negative 1 over x squared. So that's what that became. Okay? And then the limit as x approaches 0 from the right of 1 over x times negative x squared over 1. Cross cancel. And we get the limit as x approaches 0 from the right of just negative x. Now, is it safe to plug in 0? Yes. And our limit here is just 0. All of that for 0. Okay. Let's take a peek at if we put the natural log in the denominator. Just a peek, right? This is like, what if you would have the limit as x approaches 0 from the right of x over 1 over the natural log of x. That already doesn't look like fun, because now you have to rewrite it as the limit as x approaches 0 from the right of x over, putting brackets for neatness, natural log of x to the negative 1. And then, if you applied L'Hopital's to this, sure, the numerator is great. That's 1. This down here becomes negative 1 times the natural log of x to the negative 2 times the derivative of the inside 1 over x, which means we should probably just stop. So if you're coming across something as ugly as that, rethink how you rewrote the product as a quotient. So that was your what if moment. What if we never defeated Thanos? Then you have that nasty problem. Okay, so that's an indeterminate product. If you get an indeterminate product, you can rewrite the original limit as a quotient. And now we come across an indeterminate difference. If the limit of f is infinity and the limit of g is infinity, and the limit of f of x minus g of x is an indeterminate form of infinity minus infinity, then we'll do our best to convert into a whole fraction by common denominators, or maybe we have to rationalize, or maybe we have to factor. Whatever we can algebraically manipulate, that's how we're going to have to fix it. So infinity minus infinity is not 0. Remember that. Okay. So let's look at the next one. And for 7, if we plug in pi over 2. So that's where we always want to start. We always want to plug in. You get the secant at pi over 2 from the left minus the tangent at pi over 2 from the left. And now we want to know, what does those look like? And well, let's first take a look at secant. Secant of pi over 2 from the left. Secant at pi over 2 is undefined, right? So this, we'll first look at the graph of secant x. So first, if I have 0 here and then pi over 2 here, then this means that when secant's at 0, I'm at 1, so yes. So secant looks like this and looks something like that. So if we're approaching pi over 2 from the left, this means that secant is headed towards infinity. So that's what we'll write here. Secant's headed towards infinity. Minus, well, now let's take a look at tangent. Tangent at pi over 2 also has an asymptote. So here's 0. There's pi over 2. Tangent looks like this. And if we're approaching pi over 2 from the left, tangent is also headed towards infinity. Okay. That was a nice pre-cal refresher. You guys should know that stuff already, right? Okay. So with that being said, we get infinity minus infinity, which is definitely not 0. Infinity minus infinity is indeterminate, which means this just needs a little love and care at the hospital, okay? So we're able to apply L'Hopital's to it, and we get the limit as x approaches pi over 2 from the left of, and now since secant and tangent didn't work out, let's think of identities. Secant, I've been saying all day on that one problem, is the reciprocal for cosine. So secant is 1 over cosine x. Minus tangent, which happens to be sine x over cosine x. Well, what do you notice about these two fractions? They have the same denominator, which means I can write these as the limit as x approaches pi over 2 from the left of 1 minus the sine of x over cosine x. Okay. Now, here is where we want to use L'Hopital's. So I'll make the most of my room, and this will become the limit as x approaches pi over 2 from the left of the derivative of this numerator, 1 minus sine of x, that will be negative cosine x over the derivative of this denominator, negative sine of x. Okay, well, clean it up a bit. Negative and negative make positive, so we get the limit as x approaches pi over 2 from the left of positive cosine x over sine x. Okay. And yes, we can plug it in right here, which means still making the most of my room. If I plug in pi over 2, I get cosine of pi over 2 over the sine of pi over 2. And yes, it still can be from the left, but you're just going to evaluate it at pi over 2. And cosine at pi over 2 is 0. Sine at pi over 2 is 1. You get 0. And that's definitely a better answer than indeterminate. Okay. Perfect. So now you have indeterminate products, indeterminate difference, and indeterminate powers. All right. Given the limit of f of x raised to the g of x, if f is 0 and g is 0, we get an indeterminate form of 0 to the 0. Or if f is infinity and g is 0, we get an indeterminate form of infinity to the 0th. Or if f is 1 and g is positive or negative infinity, then we get an indeterminate form of 1 to the infinite power. Okay. So, with that being said, one way to fix these is to apply the natural log. We will apply the natural log, and then we'll get an indeterminate product, which means we'll have to rewrite it as a quotient, and then we can apply the L'Hopital's rule of taking the derivative. So, as we work through all of it, okay? Let's check out number 8 first. All right. 8, the limit as x approaches 0 from the right of the cotangent of x. All right. If we plug in 0, you get 1 plus the sine of 4 times 0 raised to the cotangent of 0. Well, this ends up becoming 1 plus 0, and cotangent at 0. Now you got to remember your cotangent function. Cotangent function looks like this. There's 0. Cotangent looks like that. So this means that all of this is going to be raised to the 0th. I may have that backwards. That's negative tangent. I think cotangent, does it exist at 0? That puts no. So my bad. Whoops. But even then, you'd still get indeterminate. So actually, this is what cotangent looks like. There we go. Something like that. So if you're approaching 0 from the right, the y values are headed towards infinity. So this means that that becomes infinity. There we go. That's better. Which means we get 1 to the infinite power, which is indeterminate. Okay, which means we will fix this by the use of natural logs. So here's how we start this. We will say y equals the limit as x approaches 0 from the right of 1 plus the sine of 4x raised to the cotangent of x. Okay. And then we will apply natural log. So I gotta, do I have, no, I don't have a whole page for this one. There's one more problem. Okay. Then we will apply natural logs. Natural log equal to the limit as x approaches 0 of the natural log of 1 plus the sine of 4x cotangent x. And then, by the properties of natural logs, this cotangent is coming to the front, right? That cotangent is coming to the front. Which means you'll have the limit as x approaches 0 from the right of cotangent x times the natural log of 1 plus the sine of 4x. Okay, now, if you plug in 0, if we were to plug in 0, we would now get an indeterminate product. You would get cotangent at 0, we said was infinity times the natural log of 1, which is 0. So we would get indeterminate if we plugged in now. So this means that we get to use, or not yet, almost get to use L'Hopital's. We now have an indeterminate product, which means we have to rewrite as a quotient. And like I said, keep the natural log in the numerator. So here's where we go with this. We get the natural log of y equal to the limit as x approaches 0 from the right of the natural log of 1 plus the sine of 4x over 1 over cotangent x. I keep the natural log in the numerator at all times, okay? Sweet, still got room. Okay, which means this becomes the natural log of y equal to the limit as x approaches, not that, of x approaches 0 from the right of the natural log of 1 plus the sine of 4x, and 1 over cotangent is just tangent x. That's it. Now we use L'Hopital's. So I'm going to say the natural log of y equals L'Hopital's of everything on the right side. You have the limit as x approaches 0 from the right. And now we must chain rule this derivative. So the natural log of 1 plus the sine of 4x. So that has to be chain ruled for the natural log function. So the derivative, let me do that. The derivative of that is going to be the derivative of the inside, which is going to be 4 cosine 4x. Because the derivative of 1 is 0, and the derivative of sine 4x uses chain rule as well. Derivative of sine 4x is cosine 4x times 4. So that's what we get here. Four cosine 4x. Okay. Over, since this is a chain rule of the natural log, that becomes 4 cosine 4x over the original inside function of 1 plus the sine of 4x. There we go. That's what goes here. 1 plus the sine of 4x. And all of this is over the derivative of tangent x, which is secant squared x. Now it's definitely cleanup time. Okay. Well, secant squared is the same as 1 over cosine squared x, which means that that can actually flip to the numerator. So what I actually end up with here is the limit as x approaches 0 from the right of 4 cosine 4x times cosine squared x all over 1 plus the sine of 4x. Still doing good on space. Cool. Okay, so now if I bring this back, I have the natural log of y equal to the limit as x approaches 0 from the right of 4 cosine 4x cosine squared x over 1 plus the sine of 4x. Now let's plug in 0 and see what happens. I get 4 cosine of 0 times cosine squared of 0 over 1 plus the sine of 0. This leaves me with the natural log of y equal to cosine at 0 is 1. Cosine squared at 0 is 1 squared, which is still 1. So you get 4 times 1 over sine at 0 is 0. So this is all over 1, which gives me just 4. Almost there, kids. Now you get the natural log of y equals 4. We need to solve for y. So let's do a quick refresher on natural logs and their inverses. So for this guy here, remember, if I have natural log of y equal to x, the base of the natural log is always e. And I can always rearrange from log to exponential or exponential to logarithm. So if I rearrange this, this becomes e to the x equal to y. That's all we have to do, which means that this becomes, if I put this little e here, we get e to the fourth equals y. That is our answer. Ooh, fun times, huh? Okay. Okay. Yeah, we look good. I mean, I guess I could have, dang, could have went to the right more, but oh, good. Still going. Okay, number 9. We're going to do the same exact thing. So, start it off by plugging in 0. You get 0 to the 0th, which is indeterminate. So now we introduce logs. So, well, first we introduce y. We say y equals the limit as x approaches 0 from the right of x to the x. Then I say the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of x to the x. Then again, by natural log properties, this x comes to the front, right? So I get natural log y equals the limit as x approaches 0 from the right of x natural log x. And again, if I plug in 0, if we plug in 0, you'll get 0 times the natural log of 0 from the right, which would give me 0 times negative infinity, which is again indeterminate, which means we have to rewrite it again as an indeterminate product into a quotient. Okay. So, again, keep the natural log in the numerator. Natural log x over 1 over x. And clean up. Natural log y equals the limit as x approaches 0 from the right of natural log x over x to the negative 1. We are now ready for L'Hopital. So right here, L'Hopital's coming. The limit as x approaches 0 from the right of 1 over x over negative x to the negative 2. Clean this up some more. I'll just work on this side. I'll say the limit as x approaches 0 from the right of 1 over x times negative x squared over 1. Remember that this part is the same as negative 1 over x squared, which then becomes that. Okay. Cancel, cancel, and we get the limit as x approaches 0 from the right of negative x. Now let's bring that back over here. I get the natural log of y equals the limit as x approaches 0 from the right of negative x. It's now safe to plug in 0, so our limit is just 0. But we're not done. We have to take care of this natural log. And again, you will convert from natural log to exponential. So you can put this little base of e here, and then this will become e to the 0 equals y. But anything to the 0th power, anything to the 0th power is always 1. So this whole thing just equals 1. There's your limit. Buddy, those are good ones. I like those ones. Bring back everything. Brings back everything you forgot. Okay. Practice. Here we go. Okay. So, practice. Now we know how to use L'Hopital's. We can only use it on indeterminate forms. So I'm just going to work through these practice problems as if they're my own homework. So, first thing, plug in 1. You give 1 squared minus 1 over 1 squared minus 1 and 0 over 0. So we get indeterminate, which means here comes Mr. L'Hopital, which we can take the derivative. The limit as x approaches 1, you get 2x over 2x minus 1. Plug in 1 again. 2 times 1 over 2 times 1 minus 1 gives you 2 over 1. So our limit is just 2. Our limit is just 2. I mean, sure, that could have worked if I just factored this. So I could have said, all right, the limit as x approaches 1 of x plus 1, x minus 1 over x times x minus 1, cancel. The limit as x approaches 1 of x plus 1 over x. If I plug in 1, I get 1 plus 1 over 1, which is still 2. So, or factor, we didn't even need to use L'Hopital's at all, right? Okay. Cool. Who's here? Kara. Oh, thanks. All right. Let me get through these and I can help you out. Thank you for telling me that question's dumb, though. Perfect. Okay. 2. Let's see. Plug in pi over 2. All right. Cosine at pi over 2. 1 minus sine at pi over 2. That gives me 0 over 1 minus 1, which is 0 over 0. So yes, you get indeterminate, which means we get to use L'Hopital's. All right, so the limit as x approaches pi over 2 from the right, derivative of the numerator, negative sine x over derivative of the denominator, negative cosine x. Okay. This means we get the limit as x approaches pi over 2 from the right of just positive sine x over cosine x. Which means if I plug in pi over 2, I get the sine of pi over 2 over the cosine of pi over 2. And you get 1 over 0. This is not indeterminate. This happens to be undefined. Which means we have to take a step back and look at this part of the limit. Because if you're undefined, undefined is not the same as indeterminate. So we can't use L'Hopital's again. We have to figure another way to fix it. One way is to think algebraically or trig identities. The other way is whip out your calculator and make an XY chart. I rather do the identities. So let's see if we can fix this by identities. So that means that this will become the limit as x approaches pi over 2 from the right, and sine over cosine is tangent x. Which means, think of the graph of tangent. I think I got this one down. Here's pi over 2. So tangent definitely looks like this and like that. So if we're approaching pi over 2 from the right side, the y values of tangent are headed towards negative infinity. So this means that this just equals negative infinity. And that's how you fix that. So indeterminate gets L'Hopital's, undefined gets fixed algebraically by trig identities or whip out your calculator. Okay. Still going, still going. Okay. 3, same thing, plug in 0. That's sine of 0 over the tangent of 0. Sine at 0, 0, tangent at 0 is 0. This is indeterminate. Okay, which means we get to use Senor l'hôpital, even though he's French. Oui, okay? So, the limit as x approaches 0 of the derivative of the numerator, that is 4 cosine 4x, over the derivative of the denominator, that is 5 secant squared 5x. All right, both had to be chain ruled. Now plug in 0. Four cosine times 0 over 5 secant squared times 0. Seen this a lot today. Cosine at 0 is 1. Secant at 0 is also 1. But it is squared. Doesn't matter. You still get 4 over 5. Lovely. Again. Okay. See, simple. 4. E to the limit as t approaches 0 of e to the 2t minus 1 over sine of t. Again, plug in 0. That's e to the 0th minus 1 over the sine of 0. That's 1 minus 1 over 0, which is 0 over 0, which is, you know the word, indeterminate, which means we get to use L'Hopital's. The limit as t approaches 0, derivative of the numerator. Chain rule derivative for e to the 2t. That's going to be 2e to the 2t over cosine of t. Then plug in 0. 2e to the 0 over cosine of 0. 2 over 1, which is just 2. Wonderful. Oh, my neck. Okay. 5. Again, plug them in. 1 minus the sine of pi over 2 over 1 plus cosine of 2 times pi over 2. That becomes 1 minus 1 over 1 plus the cosine of pi, which becomes 0 over 1 plus negative 1, which is 0 over 0. So again, indeterminate. Which means, you know what that means, we get to use L'Hopital. So, limit as x approaches pi over 2, derivative of numerator, negative cosine x. Derivative of denominator, we'll use chain rule, so negative 2 sine 2x. Negative 2 sine 2x. Okay. Keep going. Clean up. We have the limit as x approaches pi over 2 of cosine x over 2 sine 2x. Plug in pi over 2. Cosine at pi over 2 over 2 sine times 2 times pi over 2 gives me 0 over 2 times the sine of pi, which is also 0. So 0 over 2 times 0 gives me 0 over 0, which again we get indeterminate. Which means we get to use L'Hopital's again. And we're using it on this form. That's what's going there. Okay. Limit as x approaches pi over 2. Derivative of numerator again. So negative sine of x over derivative of denominator 2 times the chain rule of sine 2x. That is 2 cosine 2x. Giving me the limit as x approaches pi over 2 of negative sine x over 4 cosine 2x. Plug in pi over 2. Hopefully we have it this time. Negative sine of pi over 2 over 4 cosine of 2 times pi over 2 gives me negative 1 over 4 cosine of pi, which gives me negative 1 over 4 times negative 1, which gives us 1/4. Ooh-wee. Okay. There's that. Hooray, fun. Six, same thing. Plug in 1. 1 to the 8th minus 1 over 1 to the 5th minus 1 is still 0 over 0. So, indeterminate, we use L'Hopital's. The limit as x approaches 1 of 8x to the 7th over 5x to the 4th. Simplify the limit as x approaches 1 of, that's just 8x cubed over 5. Right? 8x to the 7th over 5x to the 4th, 8 over 5x cubed, plug in 1, and we'll just get 8 over 5. Yeehaw. How many did I make? Oh my goodness. Okay. They're not too bad. Okay. Timer, 6:30. Oh, wow. Okay. So Apply L'Hopital's. Well, no, sorry, not apply L'Hopital's. Plug in 0. E to the 0 minus 1 minus 0 over 0 squared. That's 1 minus 1 over 0. So again, 0 over 0. So indeterminate. Bring the L'Hopital's. The limit as x approaches 0 of the numerator. That's just e to the x minus 1 over 2x. If I plug in 0, e to the 0th minus 1 over 2 times 0 still gives me 0 over 0. So again, indeterminate. Do L'Hopital's again. The limit as x approaches 0, it's just going to be e to the x over 2. E to the x over 2, plug in 0. E to the 0 over 2 gives me 1/2. Yay. Next. 8. E to the x over 10, x cubed, plug in infinity. That's e to the infinity over 10 over infinity cubed. That's e to the infinite power over infinity, which is infinity over infinity. So again, indeterminate. Okay. L'Hopital's. Chain rule derivative on e to the x over 10. That's just going to be the limit as x approaches infinity of 1/10 e to the x over 10 over 3x squared. If you plug in infinity, you'd still get 1 over 10 times e to the infinity over 3 times infinity squared, which is infinity over infinity. So again, you get indeterminate. Bring it back. L'Hopital's again. The limit as x approaches infinity. If you L'Hopital's this part, you get 1 over 100 e to the x over 10 over 6x. Again, if I plug in infinity, I get infinity over infinity. Indeterminate. Which means probably one more L'Hopital. The limit as x approaches infinity, the derivative of that of the numerator is 1 over 1,000 e to the x over 10 over 6. Oops, oh well, different color. If I plug infinity in, I would still get infinity over 6, which means this whole thing just goes to infinity. There's our answer after all of that. Okay. Nine. Going. Plug in 0, you get 0 times 3 to the 0th over 3 to the 0th minus 1. that just becomes 0 over 1 minus 1, 0 over 0. Indeterminate. Okay, so that means we get to use L'Hopital's, and I get the limit as x approaches 0. And now this part is going to have to be product ruled. Because it's x times 3 to the x. So, oh, my ears hurt. So f equals x, g equals 3 to the x. F prime is 1. G prime uses the derivative for exponential functions, which is 3 times 3 to the x times the natural log of 3. Right? If I have, what is it? F of x equals a to the x, then f prime of x is a to the x times the natural log of a. So that's what we use there. Okay. Which means by product rule, in the numerator only, I get f prime g, which is 3 to the x, plus g prime f, which is x times 3 to the x times the natural log of 3, all over the derivative of the denominator, which is 3 to the x times the natural log of 3. Gross. Okay. Now, let's clean it up. Can you clean this up? No, not really. I think you can plug in 0 now, though. Let's see what happens. If we plug in 0, 3 to the 0 plus 0 times 3 to the 0 times the natural log of 3, all over 3 to the 0th times the natural log of 3. That becomes 1 plus 0 over 1 times the natural log of 3. And this is just 1 over the natural log of 3. Gross. Oh. We're going. Ten. Let's do it. 10, that becomes cosine of 0 minus cosine of 0 over 0 squared, which gives me 1 minus 1 over 0, which is 0 over 0, which is indeterminate. So L'Hopital's. We get the limit as x approaches 0. First derivative is this with the chain rule. So it's cosine of mx. So our derivative should be m, not m cosine, sorry. So the chain rule derivative of that's going to be negative sine mx times m And then the next one is the chain rule derivative of negative cosine nx. So that's going to be plus sine nx times n over 2x. Now, if I plug in 0 now, you'll get, what is it? Negative m sine 0 plus n sine 0 over 2 times 0. And all of this is just going to be 0 over 0. So again, indeterminate. So let's take the derivative again, but first I want to clean this up. This becomes negative m sine mx plus n sine nx over 2x. There. Nice and pretty. We L'Hopital's again, and I have the limit as x approaches 0 of now the derivative of that, which m you will consider a constant. So this becomes negative m times cosine mx times m plus n, which is another constant, times cosine nx times n all over 2. Clean up the limit as x approaches 0 of negative m squared cosine mx plus n squared cosine nx all over 2. Okay, now plug in 0 and you get negative m squared cosine 0 plus n squared cosine 0 over 2. And this should just leave us with negative m squared plus n squared over 2. That's it. Yay. I said, yay. Oh, last 2. Thank goodness. My goodness. Plug in 0, sine of 0 times the natural log of 0 from the right gives me 0 times negative infinity, which is indeterminate. Okay, so we rewrite this as an indeterminate. So it's an indeterminate product, so we need to rewrite it as a quotient. And for this one, I put sine in the denominator. Let's see. So natural log x over 1 over sine of x. Okay. Clean this up, and the limit as x approaches 0 from the right of natural log x over cosecant x. which means now let's use L'Hopital's. And you get the limit as x approaches 0 from the right of 1 over x over, and the derivative of cosecant, is something. Is negative cotangent x cosecant x. Negative cotangent x cosecant x. Okay, clean up. The limit as x approaches 0 from the right of 1 over x, and this would be 1 over, negative 1 over tangent x sine x. Okay. Flip it, and we get the limit as x approaches 0 from the right of 1 over x times negative tangent x sine x over 1, which then becomes the limit as x approaches 0 from the right of negative tangent x sine x over x. Okay, perfect. Now, it doesn't matter which one you split. Let's say that I rewrite this as the limit as x approaches 0 from the right of negative tangent x times the limit as x approaches 0 of sine x over x. This one we know will become 1. And then tangent at 0 actually becomes 0. So what we are left with is 0 times 1, which is just 0. So we do a lot of work here for 0. Okay. 12. Last one. Thank goodness. This is almost going to be a 2-hour lesson. Oh. Okay. So here I get cosecant of 0 minus cotangent of 0. And just like before, I think we're going to get infinity minus infinity. So indeterminate. So let's look back. Let's rewrite it. The limit as x approaches 0. Think identities. 1 over the sine of x minus cosine x over sine x, which gives me the limit as x approaches 0 of 1 minus cosine x over sine x. And now we L'Hopital's it. And you get the limit as x approaches 0 of the numerator, which is going to be sine x over cosine x. Plug in 0. The sine of 0 over the cosine of 0 gives us 0 over 1, which is just 0. Yay! My goodness. That is L'Hopital's rule, which does make derivatives a lot easier. Ooh, that was a lot. Okay, I am done.